dealing with an integer that has two conditions imposed upon it. One, it's a odd integer, and another condition is that it's not a multiple of 3. So another way of saying that would be n is equal to 3m, where m is some other integer plus 1. If it's not a multiple of 3, it has to have either a remainder of 1 or a remainder of 2. Okay. If it was multiple of 3, it would just be equal to 3m, right? So these are the only other two cases, right? N can be equal to 3m plus 1, m can be equal to 3m plus 2, because it cannot be a multiple of 3. And the only divisors when you divide an integer by 3 are 0, 1, and 2. The only remainders when you divide an integer by 3 is 0, 1, and 2. So we rule out 0 because we're right at the very beginning we're saying that n is not a multiple. In other words, another way to say this says 3 does not divide m. Another way of saying this is that let me just call it m sub 1 here. N is not equal to some multiple of 3, right? There's another way of saying this. But this characterizes it also, okay? Now, we want to show that if we have an n with these two initial conditions, that n squared minus 1 is a multiple of 6, which is what this says. So let me write down the equivalency right here. This would be the same thing as saying n squared minus 1. And we're running out of constants, thank goodness for subscripts here. We'll say that this is equal to 6m sub 2, okay? So if we can show that this occurs, in other words, if we can show that n squared minus 1 is 6 times some other integer for these two cases, we'll be done with the problem. And when we finish that, we're going to go ahead. I'll show you a concrete example also. Okay, so the odd nature of the integer says this is the usual stuff. It's equal to 2k plus 1. It's an even number plus 1. Okay, so we know that from this initial condition here. And now, as I mentioned earlier, we're going to have to go through these cases. It's not too much trouble, actually. All right, so n squared minus 1 is a difference of 2 squares, famous formula. Okay, now notice here, this works out quite nicely. If you add 1 to this guy right up here, you get 2k plus 2, which is what I've written right here, right? 2k plus 2. And then if you subtract 1 from this guy, you have 3m, right? So this is some multiple, right? I'll call this, we'll just stick with our friend m sub 2, right? Okay? So you see, for case 1, we quickly see that n squared minus 1 is some multiple of 6, since this is a multiple of 2 right here. There's a factor of 2 right here, and of course 3 is manifest. All right, now let's get to case 2. And it's very, very similar, folks. If you add 2 here, if you add 2 to 3m plus 1, you get 3m plus 3. So you see you get a multiple of 3 here. And similarly, you get 2k in a different sort of position here. And we get another multiple of 6, right? And I'm reusing, I don't think that's, some people want to use different letters all the time. Maybe there's an argument for that. But in any event, these aren't necessarily, obviously, the same M2s, you know. So anyway, that completes the proof, because in the only two possible cases, we've shown that n squared minus 1 is a multiple of 6, okay? So it's QED time, okay? We proved it. Now, let's go ahead and, I feel a little remiss to not work a concrete example. Let's take a look at maybe, we have to be an odd integer, so why don't we try out, let's say, 41. 41 is an odd integer, right? Odd integer, all right? And it's equal to 3 times 13 plus 2, right? So it would fall into this category right here, right? So it does meet the conditions. It's not divisible by 3, and it's equal to that, just explicitly. All right, now let's take a look if indeed it's a multiple of 6, okay? So we can write down 41 squared minus 1 And again, we don't even have to know what 41 squared is. It's not that 41 squared is. It's not that difficult. But notice we can just use our friend, the formula. So we can write this as 41 plus 1, right, times 41 minus 1. Right? And so what do we get here, friends? This is equal to 42 times 39. And all by itself, 42 is divisible by 6, right? Without even knowing what this is. So this is 42 times 40. But that's clearly, and I'll just go ahead and use the congruence notation here. That's congruent to 0. Mod 6. And y'all, again, it's mod 6. I don't have room to write it in here. It's already unreadable, you know. But that's because 42 is equal to 6 times 7, right? So there's an example of it working. But hopefully this was a convincing proof that it has to happen on these in this casework. All right. That is all. See you next time.